So I hope you enjoyed the lectures from Daniele. Now I'm back for the next few lectures. I'll be your instructor. So let me first recap where we are, and then I'm going to introduce the topic for today. And to do so, let's go back to our usual roadmap for this class. So far, what we've been investigating is the left-hand side branch of this complicated roadmap. That is, we have been looking at methods that solve the optimal control problem in open loop form. That is, what we are trying to compute is a sequence of controls parameterized by time that optimize a given cost function, given in additive form. And we'll be looking at two broad classes of methods referred to as indirect methods and the direct methods. These two classes of methods are really complementary. So in the case of indirect methods, the idea is to first derive necessary conditions for optimality, basically the generalization of the gradient equal to 0 condition from nonlinear optimization to the setting of infinite dimensional optimization, namely optimal control. You saw that that necessary optimality condition boils down to solving a two-point boundary value problem, that is a differential equation with split boundary conditions. And historically, that's the first methods that has been developed to solve this class of problems. And then you also saw the other approach referred to as direct methods, where the idea is to take the given continuous time optimal control problem, discretize it, and once you have discretized the problem, now you're back to the setting of a nonlinear optimization, and then use a nonlinear solver of your choice in order to solve that nonlinear optimization problem. These days, particularly for robotics, direct methods are more popular. Thanks to advances in algorithms, for example, for nonlinear optimization, advances in hardware, it's now feasible to solve these nonlinear optimization problems on the edge. Something that was not, of course, feasible, both theoretically and practically, say, back in the 60s or 70s, when indirect methods were originally conceived. That said, indirect methods still have some usefulness in the field. Sometimes they can give you a closed form solution, which, of course, is the crown jewel if you have the explicit representation of the optimal control sequence. That's great, because it takes 0 time for implementation. And other times, even though we're not going to look at this topic more deeply, there are some synergies between the indirect optimal control and direct optimal control, so the two methodologies can be hybridized. But rather than going more deeply on this topic, today we're going to switch to the right branch of this roadmap. Namely, we're going to look at methods that fall under the class of closed-loop optimal control methodologies. We're solving the same problem. The problem doesn't change. What changes is the mathematical object we are optimizing over. That is, now our goal is to find an optimal closed-loop control policy. We are no longer satisfied with finding an open-loop control sequence. Now, we want to find a control law that maps for all possible states that one can achieve at time t. It gives us, for all possible states that one can achieve at time t, the optimal control u star. Again, as I said during the first lecture, the notion of open loop and closed loop is quite natural, but sometimes might lead to some confusions. Of course, the behavior of a closed loop optimal control policy is identical to the one of an open loop control sequence in case the system follows the nominal trajectory. That is the one induced by the open loop control sequence. So you might say, why should we bother about computing a closed loop control policy? Well, something that is not accounted for in our formulation, at least in our basic formulation, is the presence of disturbances or model mismatches. So even though mathematically the problem that we are solving does involve any disturbances or model mismatches, in practice, of course, when you deploy these control laws or optimal control sequences, you're controlling a system whose underlying dynamical model is different from the one that you have used for control design. An optimal control policy, closed-loop control policy, is a more robust object because the moment that you go off the nominal trajectory, you know what to do. While in this case, you will blindly apply the control that was pre-computed for timestamp t, no matter what. Is this part clear? Sometimes it might lead to some confusions. Yes?
What is
Use R?
X.
X, the same. It maps the state wherever you are in the world. So you can think of UT as the right thing to do if you are exactly along the nominal state trajectory. But the moment that you move farther from it, you don't have any guarantee anymore that it might be the optimal thing to do. Now, to develop, now the question is, okay, so it seems true that closed-loop control policies are more robust and better in general than open-loop control sequences. How do we solve for them? So what we're going to do next is to discuss an algorithm referred to as dynamic programming that is a very procedural way to solve for optimal closed-loop control policies. Then you may say, why don't you always use dynamic programming? Well, because dynamic programming is computationally much more intensive. So on the one hand, you have something that is more powerful, closed-loop control policies, but much more computationally intensive. On the other hand, you have something that is computationally much more feasible, but less powerful. That will lead us to MPC, model predictive control, where we try to get the best of both worlds. We try to reason in terms of closed-loop control policies, but in some sense, with the same computational footprint of open-loop control methodologies. That's what we will see in a couple of weeks. So does the plan make sense for the next 2 or 3 weeks? All right. So then the task is, how do we find an algorithm that allows us to solve for an optimal closed-loop control policy? To do that, we're going to derive the algorithm first in a discrete time setting. Next week, we will extend the derivation to the continuous time setting. So for the discrete time setting, what we have is essentially the same formulation we saw during lecture 1, but now we are discretizing time. So time is no longer a continuous variable, it is a discrete variable. And each time instant is denoted by tk or stage k. The two terminologies are equivalent. Time tk could be, the discretization could be time 0, 0.1, 0.2, 0.3, or equivalently we could say stage 0 corresponds to time 0, stage k equal 1 corresponds to time 0.1, stage k equal 2 corresponds to time 0.2, and so on and so forth. Now that we discretize time, we have to discretize our update equations. That is the mathematical formalism that allow us to map the current state and control into the next state. In the original optimal control formulation, that was given by an ordinary differential equation. Now what we have is a discrete time equation, which can either be derived from the continuous time equation through discretization, or maybe it's just the most natural way to define the dynamics for your system. But in case you derive it from the continuous time equations, one very simple way to go from a continuous time update equation to a discrete one is through Euler discretization. So say that your dynamics are given by x dot equal f of x ut. Dot, remember, is derivative with respect to time. Then the derivative can be approximated as xt plus delta t minus x of t over delta t. Which means that if you want to reason in discrete time, then you have the discrete time update equation xt plus delta t equal to, is equal to x of t plus delta f of x u t. And then you define all of these as your new dynamics equation, now discretized. So f tilde will be the f here. We have control constraints, as usual. So the u's, now also the controls are discretized. You can take an action at stage k plus 1, and so on. The controls at each stage k have to belong to some set, capital U, that is also a function of x. So your control set can change depending on where you are. Control constraints could be you don't want to accelerate, you cannot accelerate beyond a certain acceleration level, or you cannot impart thrust beyond a certain thrust level, and so on. Then we have the cost function. So the cost function structure is the same as what we had for the optimal, continuous time optimal control problem. Has an additive form, so there is a term that sums up the stage-wise contribution to the cost. So this is the cost that you pay at time k if you're in state xk and you use control UK. Think about the fuel that you're spending, or maybe how unhappy you are about being at state xk. And HNXN is the terminal cost, how unhappy you are when at the end of your optimization horizon, so after capital N time steps, you are in state x of n. So this is also the discretized version that we derive when we discuss about direct methods. So everything stays the same. The main difference is that now we are interested in finding optimal closed-loop policies. That is, we want to find the solution in the form of a function pi. Star means optimal in optimization in general. That maps whatever state you're in and whatever time you're in into the optimal thing to do with respect to this cost function. Before, it would have been, when we were talking about open loop controls, the object we were optimizing over was simply the sequence of U0 star, U1 star, and so on and so forth. Not a function of the state. Now we want to find it as a function of the state. It might sound as a simple terminology. This has very deep implications, as explained before. This should make sense. What do you think? All right. So now the question is, how do we find an algorithm to find such an optimal closed-loop policy? And the key to crack the problem is to recognize that this problem does have structure. And the structure in this problem can be used to derive a fairly efficient algorithm referred to as dynamic programming. And the structure that this problem has is referred to as the principle of optimality, which is the consequence of using an additive cost as our cost function. If instead of a summation you use something else, the tangent of the sum of the stuff, that doesn't work anymore. So here you see how our formulation is a good compromise between being relatively general, but also having enough structure for us to derive usable, actionable algorithms. So what is the principal optimality? The principal optimality is a fairly simple concept. In my experience, the first time that you hear about it, you think it's obvious. If you think more about it, you get a bit confused, but then after a while it becomes obvious again. So let me state the principal optimality. This principal optimality essentially says that if you have a multi-step optimal control problem. So you're optimizing operations over multiple steps. The tails of an optimal policy are optimal for the truncated problem. I'll explain better what I mean. Let me first show a simple statement of the principle of optimality and a proof of it. So let's assume that we want to solve an optimal control problem that is abstractly represented as finding some path in some space. So suppose that you have an initial condition referred to as A, and you have a final condition referred to as E, and you want to go from A to E, and to do so, you have to enact a number of decisions. You thrust in one direction, and after a while, you thrust in another direction, you keep going, and then you get to your final condition, E. So let's assume that the optimal path stemming from the optimal selection of controls first leads you to B, and then through a number of additional decisions leads to E through this path. So this piece here is the realization of many additional control inputs. Now, let's call the cost of transitioning from A to B along this path as J, A, B. And let's call the cost of transitioning from B to E along this specific path as J, B, E. So according to our formulation, what is the total cost for going from A to E along what I claim is an optimal path? A to E. That's right, because we're assuming that we have an additive cost. So the optimal cost, J from A to E, is simply the sum of J, A, B plus J, B, E. And that stems from the fact that we formulated the optimal control problem with respect to a cost function that is additive. So what the principle of optimality is saying is that if the red highlighted path, A, first we go to B, and then we go to E along this red highlighted path. So if this path is optimal to go from A to E, then the tail of it is optimal for the truncated problem. So if I were to reformulate the problem, now starting from B. So now you should say, well, I mean, that sounds obvious. But let's prove it. So what I'm saying is that if A to B and then B to E along the red highlighted path is the indeed optimal path to go from A to E, then the tail of this path, meaning the path that starts at B and brings us to E, is optimal for the problem when started at B. And let's prove this statement by contradiction. So proving by contradiction means that we negate the claim, and we'll see that we'll come up with a contradiction with our hypothesis, which in turn proves that the claim has to be true. That is, suppose by contradiction that what I'm saying is not true. That is, for the problem whereby we start at B and we want to get to E in the most optimal way, there is indeed another strategy whereby we first go to some state, let's call it C, and then we follow a path that goes to E. If this total path is indeed the optimal one for the problem that starts at B, it means that JB going to C first and going to E, let's call this cost JBCE, is less than JBE. JBE is the cost of the red highlighted path. JBCE is the cost of going to E, first going through the state C. The cost of this different path. Well, but if that was true, it means that I would have found a better path to go from A to E. Simply the one that goes from A to B first, then to C, and then to E. Because of this, the cost of this path would now be JAB plus JBCE, which will be strictly less than JAB plus JBE because of this. Which means that I would have found a better path to go from A to E, contradicting the claim, contradicting the assumption that the ABE is the optimal path to go from A to E. So we have achieved a contradiction which proves our claim that if you have an optimal control sequence, the tail of such a sequence is optimal for the truncated problem. Does it make sense? More or less? Spend a little time to think about it. Even though this, this principle seems quite harmless, actually has profound implications. Yeah.
Is it just the tail of your sequence? Is that not true for any subset of paths? Say you have A, B, C, E.
It has to be for the tail.
Just the tail.
The tail, yes. And then, yeah, let me say for now it's just the tail, yes. So let me reformulate now the principle of optimality in the same formalism that I discussed before to state the discrete time optimal control problem. So what the principle of optimality is saying is that if U0 star, U1 star, U star, and M1 is an optimal controlled sequence, which together with X star 0 determines the corresponding state sequence X star 0, X1 star, X star n, and so on. Consider then the subproblem whereby we are at the state X star k, at time k, and we wish to minimize the truncated problem, whereby we start at X star k and we only look at the cost after time k. Then the truncated optimal sequence, so the sequence whereby we now start at the UK star, is optimal for the subproblem. Which means, like a more mnemonic way to remember this condition is the tail of optimal sequences are optimal for the tail subproblems. So you say, who cares? We'll see in a second why we do care about this. Yes?
This formulation also moves a little bit like triangle inequality or Jensen's inequality. Are these really similar ideas in different packaging, or are they actually different ideas?
I think it's even more basic idea that follows from the additive assumption that we make in the cost. You see it here. The only reason why we could make this claim is because we could assume additivity in the cost. But the way is in a weaker condition, because the only thing that we're saying is that we need to have additivity. No matter which weird space your optimization could be over. So that's why this property is so general. So the next question is, why do we care about this? So let me give you a little bit of intuition about why we care about this. So suppose that, again, we are in a setting whereby we want to find an optimal path. So the final destination is F, And suppose that an oracle is giving you the solution to go optimally from a point E to F with cost J star EF, is giving you this optimal solution to go from D to F with cost J star DF, and is giving you the optimal solution to go from C to F with cost J star CF. An oracle, the instructor, is giving you this information. And these optimal paths may be the result of the application of 324 control inputs. So there is a lot of computation that went into computing these paths. And now it's a midterm. And you have 3 minutes to answer this question. So I'm giving you now the problem of going from a B to F. And from a B, you can go to only 3 states. You can go to C directly with cost JBC. You can go to D directly with cost JBD. Or you can go to E directly with cost JBE. And then I ask you, and of course I give you this cost, and then I ask you to compute the optimal path to go from B to F. So if you knew nothing about the principle of optimality, what you will need to do is to consider each one of these options and then resolve for all possible control combinations for the tail paths. You wouldn't have a way to actually use the information that are given to you. But now you know about the principle of optimality, and the principle of optimality is telling you that if the arc BC is the initial segment of the optimal path from B to F, then C to F is the terminal segment of this path. That is, there is no reason for you to consider any further combinations of possible control inputs for the tails of problems, because you know that the tail of an optimal problem, the tail of an optimal control sequence is optimal for the tail problem. So there is no additional optimality you can gain, but further optimizing the truncated problem. So what that means is that instead of brute force solving the entire problem from the beginning, you can just do simple concatenation. So you just look at 3 options. Concatenating the initial segment with the optimal solution to the tail problem 1. Second possible initial segment with the optimal solution to the second tail problem. And third segment with the optimal solution to the third problem. So you only have to look at 3 choices as opposed to recompute everything from scratch. So that's a part where things get a bit more interesting and things might get slightly confusing, but I hope that this example clarifies it. So let's pause for example. Yeah?
Those 3 tail segments are all the same cost, CF?
No, they don't need to be the same cost. Actually, in general, they have different cost. But what I'm saying is that each one of them is optimal for the particular subproblem where I start from E, I start from either from D or for C.
Example when this wouldn't be very obvious, just because like looking at the image, I'm struggling to understand like why, if we didn't know the principle of optimality, if we started with the cost function from B to C, why we would choose them from D to F and not just from C to F.
Could you repeat the last part?
I'm just a little confused why we would decide if we were going from B to C. Wouldn't the obvious thing be to go from C to F? Like, why look at D to F, for example, if you're already doing B to C?
So first of all, there may be multiple paths to go from C to F, or from D to F, or from E to F. And here I'm just showing the optimal one. If you go from B to C, yes, sure, it's obvious, a little bit considering the principle of optimality, that the right thing to do is to go C to F through the optimal path. But what is not obvious, since each of these costs are different, and each of these costs are different, starting from B, which one of the 3 options you should choose? That's a non-obvious part. Yes, if you are committed to go to C, then yes, it's obvious that you will need. But again, it's obvious because I just explained the principle of optimality. Otherwise, that's why the principle of optimality is a bit sketchy as a concept, because it's so obvious that sometimes people really fail to fully appreciate its depth. So yes, it's obvious, but there is some cleverness into it. I'm going to give you also another example to hopefully make things even clearer. But anyway, the main point of this slide is to show how, with the principle of optimality, we can reuse computation that has already been done, either by an oracle or, as we will see, by us through a recursive algorithm, so that you minimize the amount of computation that you do overall. So bottom line is that applying the principle of optimality allows you to compare the concatenations of immediate decisions and optimal decisions in order to compute an optimal control sequence for an optimal problem that has been extended by one step. Now, then the next question is, who is solving those tail problems for you? In general, you don't have an oracle. So that's where the somewhat non-intuitive idea of dynamic programming comes in. You solve the problem backward in time, even though, of course, time moves forward in time. So you deploy your policy going forward in time. The problem is solved backward in time. You start from the end simply because at the end, the optimal solution, it's obvious. There is no solution. You are at the end. So there is nothing you should do. And the cost is also obvious. It's just the terminal cost. That means that you know the terminal cost, you know the optimal solution at the terminal stage. But now we have a procedure to go one step at a time backward, but just concatenating immediate costs with the solution to the tail problems. The first time you do it, you just have the terminal cost. And these are boundary conditions given to you. And then you start applying recursively this idea. And for the rest of the lecture, I'm going to give you a bit more intuition about this procedure, which is extremely general. But let me start with one example where we're going to do these backward recursions by hand. And this example is more mechanical, just to show the mechanics of it. But then later on, we're also going to explore how much computational savings this buys us. So now we have a shortest path problem that is a bit more concrete. We want to start from A, and we want to go to H. And the transitions that are possible are denoted by these arrows, which means that if you are at B, you can move right to state C with cost equal to 9. Or for example, if you're at C, you can move only right. Actually, no, you can move right to F with cost 3, or you can move upward with cost 5. So the question is, what is the best path to go from A to H? If you knew nothing about dynamic programming, what you would do is to compute all possible combinations. So you go down, you go right, you go up, that's one possible sequence. You go right, that's another branch of your sequence. You consider all possible combinations that are feasible, and then you pick the one with minimum cost. Now, actually, we're going to use the principle of optimality to be a bit more principled in how we do search. Specifically, we start from the back. So what is the cost for the shortest path problem, whereby we start at H? So that's a tail problem, where we start at H. So what is the cost? We are at H, and we want to go to H. 0. Great. So we know, actually, the solution to this tail problem. So now let's go one step backward. For example, here, G. So what is the cost of G? So the cost of G is equal to the immediate cost, 2 to go upward. And then I have the tail problem that starts at H. I don't have to resolve for that problem. I already have the solution. So this would be the 2 plus GH, but I have already solved for H. H is equal to 0. So the optimal cost is 2. So let's assume that now we are at F. So what is the optimal cost to go from F to H? Well, it's the immediate cost, which is 3, plus the cost of the tail problem, which is also referred to as cost to go, which is J of G, which is equal to 2. So this is equal to 5. And then we go one step backwards. So now we have a J of E. So E is a kind of interesting case because we have two options. So remember the more abstract figure that I had before? I have two options. I can either go right. I have an immediate cost equal to 8, and then I transition directly to H. So the cost of this path would be 8 plus J of H. But then I can also go down, incurring cost 2, and transition into state F. But I don't have to recompute what is the optimal thing to do from F. I already have computed before. So this will be 2 plus J of F. This is correct. So 8 plus GH, 2 plus GF. So GH already computed. So this is equal to 0. GF already computed. This is equal to 5. So now I just pick the minimum between 2. So this is equal, the first path is 8. Second path is 7. So I pick the path that goes to F, and the cost will be 7. Then I go one step backwards. So I have J of D. So this is equal to 3 plus GE. GE already computed, so this is equal to 10. Then I have C. So J of C is equal to the minimum between 3 plus JF and 5 plus JD. No need to recompute JD. I can recycle the fact that I already solved for the tail problems. JD is equal to 10. JF is equal to 5. So 3 plus 5 is 8, 15. So the optimal cost is 8. Yes. Then JB is equal to 9 plus JC. So this is equal to 17. And finally, I hit my initial condition, A. So I have two options. I can either go right, 8 plus JD, or I can go down 5 plus JB. JD already computed is equal to 10. JB already computed equal to 17. 10 plus 8 wins, so optimal cost equal to 18. And now I can backtrack what the minimizer was at every stage of the optimization. So from A, we selected this one as a minimizer. So from A, we want to go to D. From D, we have only one options. We go to E. And from E, this was the minimizer, we go to F, from F to G, and from G to H. Yeah.
How did this become? discretize the steps? Like, for instance, how do we know that from B to H we have both cross state, and there isn't a study between another step and this?
Yeah, great question. So, in order to run dynamic programming, you have to put your problem in the mathematical formalism that I explained before. So here we will need to define states and time steps in terms of how many steps before we hit the final condition. And there are ways to actually formulate the shortest paths in such a way. So the K, the index, will be the number of steps to get to your destination H. So in other words, we want to, that's actually the tricky part of dynamic programming. That's where dynamic programming gets tricky. I'll get to you in a second. Dynamic programming gets tricky in the following way. Once your problem is defined in the canonical way, so you have a discrete time equation for your dynamics, and then you have an additive cost for your optimization problem, then, at least conceptually, the algorithm is trivial. You solve a recursive algorithm where you start from a boundary condition whereby you set the optimal solution to the tail problem, that is the problem that starts at the final condition as the terminal cost, and then you iterate one step backward until you reach the initial state, x of 0. At each iteration labeled by the time step k, you solve a minimization problem whereby you're trying to solve for a given state x of k, the optimal control, the best compromise between immediate cost and so-called cost to go, so the cost of the truncated problem. And as you can tell, I mean, this is very simple to implement conceptually. But there are a few caveats. First of all, there are a number of problems that at the first look, they seem to be completely different from the way that I'm stating the problem here. And that's where the cleverness of the designer goes. You map those problems into this formalism. And even though I haven't shown you, but I think we'll have a homework, otherwise I will put a reference on Canvas. There is a way to map the shortest path problems exactly in this formalism. So that's the first caveat. So there is some work, and we'll see a couple of examples whereby you take a problem, for example, even DNA sequencing, that at first value seems has nothing to do with dynamic programming. You can put in this formalism, and once you have the problem formulated in this formalism, you can just run the algorithm. So you say, okay, then it's more of a modeling exercise. No, it's also an algorithmic exercise, because even though dynamic programming allows you to decrease substantially the amount of computations with respect to brute forcing the computation, keep in mind that you have to carry out this optimization problem, whereby you're trying to find the optimal control at time k that optimizes this cost function. You have to do that for all time steps and for all possible states. And even though time has been discretized, technically the state hasn't been discretized. So in principle, this could be a continuous quantity. So you cannot even run this recursion because you would have infinite many of these recursions. Or even if you discretize it, you might have a very large number of possible state combinations. Let me clarify this a little bit. So say that say that your state is one-dimensional, belongs to the interval 0, 1, and you are discretizing with the 0.1 step. And say that the time is also between 0, 1, and you also discretize it with a 0.1 step. So how many dynamic programming recursions, meaning how many of those optimization problems you have to solve? Per step, you have 10 for each possible value of the state. But then you have 10 time steps, so you have 100. Okay, so you have 10 times 10. Now, let's assume time stays the same. But let's assume that now we go into the setting whereby x is two-dimensional. So, for example, position and velocity of a double integrator. How many dynamic programming recursions you have to carry out? Per each time step, how many possible combinational states do you have? That's right, so we have 100. So now you have 10, which is the number of steps, times 100. So now let's assume that it's three-dimensional. So now x is 0, 1 cross 0, 1 cross 0, 1. So basically you are optimizing over three variables, x, y, and z. So now you have 10 times steps as before, but now you have 10 times 10 times 10. So basically your dynamic recursions scale with 10 to the power of d, where d is the dimension of your state. So you have an exponential scaling. So even though dynamic programming, and you can show this more formally, dramatically decrease the amount of computations that you have to carry out, still, in general, you have to carry out a lot of computations, particularly in high-dimensional state spaces. Anyway, so assuming that you can do that, so two main challenges. A modeling one, whatever problem you are, it's possible that you can map it into, not all problems, of course, can be mapped into this formalism. But there are some problems that at face value may not look like they're amenable to this formulation, but they are. So there is a little bit of cleverness that goes into that. And then there is, of course, work that goes into making sure that you can run dynamic programming recursions at scale. So this is the topic of so-called approximate dynamic recursion that will also lead into the second part of this class referred to as learning-based control. Now, assuming that you can solve this problem, then you can construct an optimal policy by essentially bookkeeping for all possible states associating the optimal control that you have picked, and so you are incrementally building the optimal control policy part. So there is a lot here. This is a very fundamental result in controls. It's the basis of discrete time, closed loop optimal control, continuous time, closed loop optimal control, learning-based control, and policy learning. So everything exciting that you hear these days about policy learning, vision language action models, all that stuff is rooted in this equation. Of course, with many generalizations. Now, if you think about this equation, we derive it somewhat formally by basically stating the problem, stating the principal of optimality, and then just applying it in order to derive this recursion. But if you think about it, it's quite natural. So what this is saying is that assuming that you are a given state, the optimal thing to do right now is what minimizes the impact of that action on your immediate costs, plus the implication of what you do today in terms of what will happen tomorrow, starting from tomorrow. If you think about it, this is very natural. Why are you here today and not on a beach? Because you are trading off your immediate gains with future gains. Of course, going to the beach to have a nice swim in the ocean improves your cost right now, but has implications about your future education, right? So your cost to go is affected. So actually you are here because you are sacrificing your immediate wealth in order to optimize your future wealth. So that's what dynamic programming is doing. It's really compromising the immediate gains with the implication of what you do today starting from tomorrow. And it's doing so in a mathematical derived way that is principal. Yeah?
Confused about how we end up reaching our initial condition, because like if you have a final condition that's really far away from your initial condition, I don't understand how, like, especially at the beginning, it doesn't seem like there's any way the optimal solution would drive in any way towards it.
Yeah, that's why you solve backward. So you start backward, and then, I see what you're saying. So when you have x0, you are solving actually the problem for all possible initial conditions. And then you give me the initial condition you're interested in, and for that one specifically, we find an optimal control policy. But in a way, you're right. So the dynamic programming problem, to solve the solution, to find the solution to the problem that you really care about, the one with a specific initial condition x0 equal 1, 3, is actually solving all the tails of problems and all the full problems for all possible initial conditions. Or maybe you, at the last iteration, you can just be smart and only carry out this recursion for jx0. But in general, for all the intermediate steps, you have to solve the tail problems from all possible states that are reachable, because you don't know from the initial condition you're interested in which intermediate states you'll be visiting. So in that way, it's a bit wasteful. But the good news, though, is that at least it still saves quite a bit in computation. And then if problem data changes and initial condition changes, you have solved the problem for all possible conditions.
It seems that in the previous example, we were sort of processing nodes in a specific order.
Yeah, that's basically the equation under V. So what I have not shown, and I'll provide a reference, it's a bit convoluted, but not too convoluted. What they did was a bit ad hoc, but you can actually map a shortest path problem computation exactly in this format. And I'll post a reference on Canvas.
So like in general, do you also need to determine some sort of type of ordering?
Yes.
Process the states?
Yeah, because you need to put it in that formalism. And the ordering there is the number of hops we are optimizing over. So we first optimize over paths that reach the final destination in 1 hop. Then we optimize over paths that reach the final destination in 2 hops. We then optimize, et cetera, et cetera. So in the case, the number of hops is the number of stages. Okay. So a few comments. So I already talked about the discretization aspect. So that's basically how we formulate the problem. We went from differential equations to difference equations. We talked about how the dynamic programming recursion has to be carried out for each possible value of the state. If the state is continuous, then we have to quantize it. Dynamic programming actually is trying to find a global minimum for each dynamic programming recursion, so it's going to give you the globally optimal solution. If there are constraints, typically constraints make the optimization problem much harder, as you saw with direct methods and Lagrange optimization. But in this case, constraints actually make the problem simpler because they reduce the number of actions, roughly speaking, you have to optimize over. So you have less things to consider. It gives you a solution in closed loop form, but it is affected by the Karst dimensionality. What the Karst dimensionality refers to is the exponential scaling of the number of computations needed with respect to the dimension of the state space.
I have a question on the principal optimality where you said that it's only the tail some path that is like the shortest path. Isn't it true that if that's the global minimum, that any like subpath, with like regardless of whether it's the tail end path, is also the shortest path here?
Yes, I mean, but that's the principal optimality. Yeah, absolutely. Every tail path is going to be optimal. Yes. So we started from the optimal problem formulation. We derived that the most essential structure that this problem has refers to as a principal optimality. We argue how leveraging this structure, we can find an actionable algorithm to solve these problems. This algorithm has a quirk. The quirk is that it involves doing computation backward in time. And there is a nice quote from a philosopher that is loosely, actually this philosopher lived before Bellman that introduced the non-optimality principle, but it's kind of nice philosophical association, let's put it this way, that life has to be lived forward. That's obvious because time goes forward in time, but can only be understood backward. I don't know how much you resonate, but sometimes, you look at where you are, you see, shoot, I didn't realize that decision that I made 4 years ago would have led me here. So that's how I understand things backward. I don't know. It reminds me of this quote. It's up to you if you resonate or not. One thing, for your exam, very likely that I will ask you to compute one step of a dynamic programming recursion to make sure that you understand what to do. It's going to be relatively simple. It will take 5 minutes. What I'm saying is make sure that you internalize what one step of a dynamic progression algorithm entails.
What is it about this dynamic programming approach that makes it close to, as opposed to what we were learning last week?
Yes, that now we are solving problems for all possible tail problems from all possible states we could reach. That's a completely different mindset from what we were doing before. By doing so, you're basically computing an optimal control for each possible state you are in, which is really a definition of a closed loop optimal control. So this different view, different with respect to what we had before, that allows us to compute closed loop control policies. So a significant shift in mindset. All right, so let's wrap up this lecture with by solving a relatively simple but extremely foundational optimal control problem, which is referred to as a LQR, linear quadratic regulator. So the LQR problem is a specific class of discrete-time optimal control problem defined as follows. Our dynamics are linear, so sk plus 1 is equal to axk plus buk. X is the state, U is the control. A is a given matrix of numbers. B is also a given matrix. Does not depend on the state, does not depend on control. This is referred to as the state matrix. This is the input matrix. The cost is additive and is quadratic. So we have a terminal cost, which is a quadratic form in terms of the terminal state x of n. And then the stage-wise cost is quadratic too. It is a quadratic in terms of the state and is a quadratic in terms of the control. U square basically models how unhappy you are about using control U. X square is basically telling us how unhappy you are about being in state X. Since you are squaring the state, you can see how here the objective, what this objective is essentially modeling is that you want to go to the origin where the state X is equal to 0 so that you don't pay any cost. And you want to do so with a control U that minimizes the sum of the U squares. So you want to basically minimize energy. And of course, there is a little bit of a conflict here. Maybe with a larger U, you might get to the origin quicker, but then you have a bigger control effort. But then if you make smaller steps, you'll eventually get to the origin and you pay less control, but you are very unhappy for a lot of steps because you are far from the origin for a lot of steps. So basically, it's time to find this balance. This problem is referred to as a regulator because essentially it's modeling the problem of getting to the origin with minimum cost. Now, for this quadratic cost to make sense, we are requiring that the H, Q, and R are positive semi-definite, so that these are actually non-negative terms. As we will see later, we are also strengthening the condition for R to be positive definite. So this is the control penalty, this is the state penalty, and this is the terminal state penalty matrix. Does the problem make sense? As stated, it doesn't seem to be a particularly useful problem. I mean, we want to get to the origin, but in general, who cares about getting to the origin? As we will see, actually, this problem formulation is extremely useful and popular. It can readily be used in the context of trajectory tracking problems, as we will see on Wednesday, and also as a useful algorithm to even solve a nonlinear optimization problem through successive linearizations. So even in the most complicated, say, end-to-end models for autonomous driving, chances are that your tracking, where you put vision, language action models, world models, foundation models, what have you, chances are that your trajectory tracking algorithm is somewhat LQR derived. So there's an important concept. So we're looking at this problem for two reasons. One, because it's an important class of problems, especially as we will discuss on Wednesday. But two, is also one example for me to showcase dynamic programming. Why? We are exactly in the setting of dynamic programming. We have a discrete time equation, and we have a cost that is additive, which means we can solve the problem with dynamic programming. How does it work? Well, there is not much cleverness that goes into the solution. You start with a boundary condition, basically the cost at the end. So if you're in state x of n, the cost is simply 1/2 xn transpose h at x of n. And also, let me denote as a definition this cost with 1/2 xn transpose pn xn. So basically, I'm referring to h as pn. This will become clear later. For now, just remember. Of course, we want to solve the problem from the perspective of x0. But to do so, we have to run dynamic programming. So we start by going one step backward. So now we say, for all possible states that are reachable at time n-1, I have no clue which state the optimal state trajectory will go through. So I have to consider all possible ones that are reachable from x0. So for each one of them, let's call each one of them xn-1. So if this is one-dimensional, and between 0 and 1, discretizing with the step 0, 1, I would do it for state xn equals 0, xn is equal 0.1, 0.2, 0.3, all the way to 10. Well, for each one of them, I try to find a control at time n-1 that minimizes the immediate cost, which is the quadratic in xn-1 and the quadratic in un-1, and the optimal cost to go. So j star n x of n, which in this case is simply xn h xn. The cost of the problem for the state I transition into, which will be a problem at the next stage. Okay, so but x of n is simply given by a n-1, x n-1 plus b n-1, u n-1. So I plug this relationship in here. And as you can see, now this optimization problem is just an optimization problem with respect to the variable u n-1. X n-1 is fixed because for each dynamic programming recursion, you are doing it for the specific value of x n-1. Q, R, A, B is all, and H is all problem data given to you. The only quantity that is a variable here is u n-1. But this is a problem that is very simple to solve. It's just a quadratic in u n-1. We have a quadratic term coming from here. And here, so what is this quantity? So we have a n-1 x n-1 plus b n-1 u n-1 transpose h a x n-1 n-1 plus b n-1 u n-1. So this is equal to, well, we have the quadratic in u n-1, so we have u n-1 transpose b n minus 1 transpose h b n minus 1 u n minus 1. So that's the quadratic in un minus 1. Then we have the quadratic in xn minus 1. So this plus xn minus 1 transpose an minus 1 transpose h an minus 1 xn minus 1. And then we have the cross terms. So we have a plus un minus 1 transpose b n minus 1 transpose h a xn minus 1 plus the other term plus xn minus 1 transpose a n minus 1 transpose h b n minus 1 u n minus 1. So you have a quadratic in u, linear in u, and then non-dependency in u. So now to find the minimum, you take the derivative with respect to un minus 1. So we also have the quadratic here in u, and then we have non-dependency in u here. So when you take the derivative with respect to u, this goes away. This is a quadratic, so the derivative with respect to u is simply ru. Remember, there is a 1/2 that's multiplying all of that. And then I'll leave this as an exercise for you, but then you take a derivative, take a derivative of all this stuff here. So here you're left with term that is linear into u, b transpose h b u, b transpose h b u. And then you take the derivatives with respect to the terms that are linear in u, so this guy and this guy. And then you sum them up. Remember that you have a 1/2 in front of all this stuff, and what you get is b transpose h a xn. I'll leave it to you, the detailed computation is super easy. And then that's a necessary condition for optimality. You get to the second order derivative to find the sufficient one. So taking another round of derivatives with respect to u, the derivative of this term with respect to u is r. The derivative of all this term with respect to u is b transpose h b. And this stuff is positive definite because we assume that r is positive definite. So what is the optimal u? Well, is the one that satisfies the necessary optimality condition. So you solve for the first equation in terms of u. So you group everything in terms of u, and then you take an inverse. So I'm not going to throw all the steps because it's really simple algebra. The inverse exists because r is positive definite. So this entire object is positive definite, which means the determinant is non-zero. You can take the inverse. Okay, so we have found the optimal solution. And look how, that's the interesting part here, that this optimal solution is going to be given by an ugly multiplication of matrices. But this is system data, stuff that is given to you, times the state. So actually the optimal control is a linear feedback on the state. It's just a sum matrix F times X. Great. Makes a lot of sense. And of course, there are deeper relationships with the linear controls. So Fn minus 1 is defined as the multiplication of all these matrices. Okay. But then what is the cost for the tail problems? So we plug back in the optimal control input as we computed into the cost. So now we plug u equal fx back into here. So this would be x transpose n minus 1, f minus 1 transpose r, fn minus 1, xn minus 1. So you plug all that in. And again, I'm not going to go through the steps. If you don't trust me, you can go through them. But basically what I get is a quadratic form in terms of the state xn minus 1. Just do it as an exercise. You pick u equal fx as the optimal solution. Go back into the cost function with that form of u, and what you get that the cost is a quadratic in x. So then you start seeing some pattern. We started with a quadratic cost, xn minus 1, h xn minus 1. Oh, actually, I said, no, for terminology, let's call that hpn. So we started with a cost that was quadratic, xn minus 1 transpose pn xn minus 1. I found that for going one step backward, the optimal control is linear feedback on the state, and the optimal cost for the tail problems is a quadratic in the state. So what happens if you go one step backward? You started with a quadratic optimal cost to go, and you ended up with a quadratic optimal cost for the tail. So if you go one step backward, what do you think is going to happen to the cost? It's going to be quadratic, cubic, we don't know. Mathematically, the problem has exactly the same structure. So you're going to be faced with exactly the same problem you are formulating, just that now instead of having n minus 1, the subscript, you have n minus 2. Which essentially means we found a very nice pattern where we can solve this problem by recursions, but instead of solving an optimal problem, an optimization problem at each step, you just solve a recursive equation on the matrices Fk and Pk. So you start from a boundary condition setting Pn equal h. Then you set the gain for the optimal control f of k equal to all this stuff. This is stuff that depends on problem data or stuff that has already been computed at the previous step. Given the gain, then you compute the cost from the perspective of time k by updating pk according to this relatively ugly but simple to implement equation whereby you are just multiplying the problem data and stuff that has been already computed. And then you go one step backward. Does it make sense? So it's just one lucky case whereby the dynamic programming recursion boils down to a recursion on some matrices. These equations actually are very important in control and are referred to as Riccati equation. Riccati was an Italian mathematician. So as you know, I'm originally from Italy, so I do care that you spell Riccati correctly. So Riccati is 2 C's here and 1 C. For whatever reason, I don't know why in the United States, oftentimes, this is referred to as either Riccati or Riccati. By the way, Riccati in Italian means blackmailing. So, not this one, not this one, this one. Okay? Riccati. 2C, 1T. Great. So, bottom line here. So, we discussed the foundations of closed-loop optimal control. We discussed how, by using fundamental structure in our problem formulation, referred to as the principle of optimality, we can derive an actionable algorithm, referred to as dynamic programming. Dynamic programming is purely procedural, means that once you're given the problem formulation, you just write down in Python, these days maybe you use Claude, to write your recursion. That's the easy part. The hard part is on the modeling side, making sure that your problem is efficiently formulated in the same formalism of the optimal control formulation. I'll share a pager that shows you how to do that for the shortest path problems, since there were a couple of questions today. And of course, doing dynamic programming at scale requires a number of approximations that we will discuss later on in this class. That's the hard part of dynamic programming. We look at a special case of dynamic programming, which is dynamic programming applied to LQR. LQR is a problem of its own interest. As we will see, particularly on Wednesday, has a number of very useful applications in robotics and controls, tracking, nonlinear optimal control, and we'll see. And the beauty of LQR is that the dynamic programming recursions simplify into recursions about just two quantities. The gain matrix for the optimal controller, which is provably in the linear feedback form, and another matrix P that tells you the cost for each tail subproblem. And of course, LQR was also a way for me to give an example about carrying out the dynamic programming recursion. Make sense? So what we're going to do next is then, so on Wednesday, is to see how LQR can be applied to a number of additional problems that are very, very useful, particularly in robotics. All right, see you on Wednesday.